Hey, you certainly know how to divide two numbers. But what if the numbers are not exactly known and are only given as estimates through intervals? How do you calculate, for example, this division here? Well, the result will be shown in a few minutes. But first, you probably want to understand the basics of the other fundamental operations in interval arithmetic. For example, if x is a number between 1 and 3, and y is a number between 4 and 5, then x plus y lies within an interval formed by the sum of these two intervals. To express the result, which is an interval, I need the smallest possible value for the left endpoint and the largest possible value for the right endpoint, which can result from adding any values from these two intervals. In this example, it's easy to see that the smallest value is 1 plus 4, which is 5, and the largest is 3 plus 5, which is 8. Since the endpoints of the intervals represent the smallest and the largest possible values of these intervals, no other combination of numbers within the intervals can yield to smaller or larger results. So the result of x plus y is in this interval. In general, for any real intervals, the sum results from adding the left endpoints and the right endpoints. Kind of logical, isn't it? Okay, what about subtraction? The smallest and largest possible values are also easy to see here, namely 1 minus 5 for the left endpoint and 3 minus 4 for the right endpoint. In general, the difference between the first and the second value and the second and the first value, respectively. For multiplication, as you might guess, we also look for the smallest and largest values that can result from multiplying any values from these two intervals. In this case, the left and the right endpoints are multiplied to obtain the result interval. However, in this case, actually different combinations, namely 3 times minus 5 and 3 times 4, lead to the smallest possible interval covering all possible results of the individual products. And there are many more intervals where different combinations lead to meaningful results. Therefore, for multiplication, any product of the endpoints can lead to the smallest or largest value and must be considered individually. Generally, the left endpoint is formed from the minimum and the right endpoint from the maximum of all possible endpoint products. In the first case, the minimum and the maximum of these combinations are 4 and 15, and in the second case, the evaluation of the combinations results in minus 15 and 12 respectively. Well, you can probably guess how it works for division. Exactly. Again, we look for the smallest and largest value that can result from dividing the boundary values. And as with multiplication, depending on the intervals, different combinations can lead to the smallest possible interval that covers all possible results for this operation. For example, here it's 1 divided by 5 and 3 divided by 4. And here it's a different combination that leads to the correct result. Generally, we'll look for the minimum and maximum of the 4 quotients. In the first case, we're looking for the minimum and maximum of these quotients to obtain our result intervals, and in the second case, we are looking at these quotients. And as you certainly know, we don't want to divide by 0. That means 0 must not be included in the second interval. Let's break it down in a more mathematical way to make it look cool. An arbitrary real interval A with boundaries A1 and A2 is nothing more than a set of all possible real values. Let's call them, for example, x. For these elements, the following holds. X is greater than or equal to A1 and less than or equal to A2. The same applies to some other interval B. So, if we combine both intervals through an arithmetic operation, A circle B, where this circle often represents plus, minus, times or divided, the result is again a set containing all the combined elements for this operation. With x and y still fulfilling their conditions. And this set itself is nothing more than an interval. Since I need the smallest and largest values to represent this interval, I simply have to look for the minimum and maximum of the possible combinations of the boundaries. This is the general representation, called the classical interval arithmetic, and it applies to all four basic arithmetic operations we have considered here. It's just that for addition and subtraction it becomes a little bit simpler. It's pretty convenient to represent this in just one line, isn't it? Well, if you're a software engineer, for example, you know what I mean. Right, with this knowledge, let's go back to our initial example. But to make it a little bit more engaging, let's wrap it into the following task. Provide the interval containing the possible zeros of the following set of functions. Okay, set the equation equal to 0, solve for x, bring the minus into the interval, swap the left and right boundaries, since the smaller value is always on the left, and voila, our quotient appears. Remember? And now you know how to solve this fraction. You take the minimum and the maximum of the quotients, and bam, the zeros lie within this interval.